Integration by parts can help out in some surprising situations. Here's a classic example of this. Let's find the integral of e to the x times sine x dx. So this might seem like a crazy function, but in fact it comes up in a lot of physical situations, so it's actually kind of important to know what the antiderivative of this function is. This function shows up in harmonic oscillation, which is a very common physical situation. So to figure out what this antiderivative might be, we have to dream up a technique of integration that might help us. Right? Definitely we aren't going to be able to guess an antiderivative for this. And a u substitution seems unlikely to help because there's no obvious inside piece other than x, but that wouldn't make a very good u substitution. It seems like the only thing we could do here is, since there's a product, we could use integration by parts. So let's give it a try. First we have to decide what is going to count as u and what is going to count as v. So u we're going to differentiate. So which of these would we rather differentiate? Well, neither of these get more complicated when you differentiate, and also neither of them get more complicated when you integrate. So really it sort of seems like it doesn't matter which one you choose for u and which one you choose for dv. So I guess for u, let's choose sine. And that means du is cosine x dx. That means dv is e to the x times dx. And v is e to the x. So now we can write integration by parts. So this equals, I'm leaving some space here for a reason. This equals, so u times v, so e to the x sine x minus the integral of v times du, so e to the x cosine x dx. Okay, so we did integration by parts. As usual, it transformed one integral into a different integral. Now we have to ask ourselves, is this new integral any better? Well, I mean, it seems like we haven't made progress, because turning sine into cosine doesn't make this integral any simpler. It just makes it different, right? So it's hard to know what to do, and if you spent enough time thinking about it, or if you were just taking random stabs in the dark on what you might try, you might think, well, let's do integration by parts again, I guess. It's still a multiplication, so why not give it a shot? Still, we have to decide what is going to count as u and what is going to count as dv. If you switch which is which, so if you say that u is e to the x here, it turns out you just get back to this integral in a way that, back to the original integral in a way that isn't helpful. So let's not do that. For u, let's take cosine x, and for dv, we'll use e to the x again, dx. So du is negative sine x dx, and v is e to the x. So when we do integration by parts, we get e to the x sine x minus, and then let's write out our integration by parts. So u times v, e to the x cosine x minus integral of v times du, so don't forget this minus sign right here, minus e to the x sine x dx. Okay, now we can take this minus sign here, take it outside of this integral, and make these pluses. So what we get is e to the x sine x minus e to the x cosine x minus, so now I'm distributing this minus sign, minus integral from e to the x, or of e to the x sine x dx. Okay, now this probably seems like a giant failure because look, we haven't made any progress. We've gotten right back to the original integral, right? We started with the integral of e to the x sine x, and we did integration by parts and we got back the exact same integral. So what's the deal? Was this a big waste of time? Well, no, this wasn't a waste of time because if you look at the right-hand side, the integral that we want has a minus sign in front of it. So we could treat this unknown integral as an unknown thing and solve this equation for it. So let's add to both sides the integral of e to the x sine x dx on both sides here. So what do we get? On the left-hand side, we just get this integral plus itself, which is twice that, so 2 times the integral of e to the x sine x dx. And then on the right-hand side, e to the x sine x minus e to the x cosine x. And these, the minus the integral and plus the integral on the right-hand side, of course, those cancel and they're gone. On the right-hand side, we don't have a constant of integration because our indefinite integral on the right-hand side canceled. So now we need to write out that constant of integration, right? As soon as one side of your equation doesn't have a constant of integration, you need to write it. So there we'll write plus c. And finally, we can finish getting our unknown integral just by dividing by 2. So the integral of e to the x sine x dx is equal to 1/2 times e to the x sine x minus e to the x cosine x plus a constant. So, right, we're dividing this c by 2, so we could call c over 2, we could call that, I don't know, c hat. So, c hat, right? Since c is an arbitrary constant, dividing it by 2 gives you just as arbitrary a constant. So, so here we were able to get this tricky indefinite integral by using integration by parts twice, which gave us an equation that we could then solve for our unknown integral. You can find the integral of e to the x cosine x using the same trick, but I'll leave that as an exercise.